All right, so before we finally leave the SCR topic, I want to just emphasize that SCR-based metrics, I think at the end of the day, you want to use them for screening in some way, not for making final decisions, unless it's a very blatant thing. Like if you have an SCR of 0.7 and somebody wants to connect and it's a very simple case, it's a red flag that's strong enough that you can say, no, pass on that one, right? But most of the time it's not that clear, especially if you're using more advanced metrics. And so those should be used and carefully tuned using detailed studies. So what an SCR-based analysis should tell you is, do I study this or not? You know, and when I'm saying study, I mean EMT study, something detailed that can give you all of the control interactions and everything else. That's what an SCR type analysis does, is it points you towards more detailed studies. It's not a detailed study usually by itself. Okay, just remember that. Okay, so now leading into this, when should we be doing an EMT study? It's obvious that we can't always do EMT studies. We can't even most of the time do EMT studies unless you're in a very special kind of region, usually smaller regions, island systems, radial systems, systems without too many IBRs or too many interconnection requests. That's a relatively rare animal these days. So most of the time we have to decide. When you're deciding when to do an EMT study and how big of a model you should use, how complicated of a model you should use, we need to ask two related questions. Or these are two related questions, and the answer to the questions is going to be enough of an it depends that you're going to be unhappy with me at the end. This is something you're going to, of course, have to think about yourself and decide for yourself, but I'll try and give you some help in that thinking, okay? Will most studies benefit from EMT? Yes. EMT is very detailed. It will give you insight into your plant and into your system that you wouldn't get any other way. And so most studies or most interconnections, for example, will benefit from it. But that doesn't mean we should always do it, right? So here's your hypothetical. I've got two systems. The first one has a 50 megawatt IBR with a short circuit ratio of 2 at that location. And then it's connecting into TSO number 1, which has a 500 bus network and a 200 megawatt peak load. Okay, so an island system. They have one engineer and 2 months to finish a study. We're going to go to ISO number 2, TSO number 2. The same plant is connecting in with the same short circuit ratio, 50 megawatt IBR, short circuit ratio of 2. They also have a 1,000 megawatt IBR with a short circuit ratio of 2, and a 1,500 megawatt IBR with a short circuit ratio of 1.5, a much bigger system, 10,000 bus, and one engineer available, and 2 months to perform a study. 2 weeks? Dennemeyer gave me 2 weeks to perform a study, not 2 months. And he's actually probably right. Okay, 2 months is luxurious. Let's say 2 weeks, but let's say 2 months. So which one should study the 50 megawatt IBR? Of course, it's the same plant, the same risk that that plant will go unstable, the same benefit that can be derived from the study, but one of them has bigger fish to fry, right? And so they're going to focus their efforts on the more difficult one. So these are the same situation where your utilities have to make a different decision about what to do related to EMT studies. They have to focus their effort. So every utility in every region has unique problems and challenges. Variables include the availability of human resources and training expertise. These days could be availability of consultants, right? The strength of your system now and into the future. And this is a double-edged sword. So if you have a very strong system, it means you have more time to figure this out. It doesn't mean the same problems aren't coming for you, but bigger. Okay? So it's like a truck that's further away, but a much bigger, faster moving truck. So the ones that have a problem now tend to be the smaller utilities with interconnections coming into weakest part of their system. In the future, and actually the future is in some cases now, the big utilities have now added enough renewables to their plants or to their systems that they're going to start to see the same problems, but they're not necessarily equipped for that. How much time do you have to do it? How much of the models do you have? Have you been collecting these models as recommended by NERC and others for the last 5 to 10 years? Or have you not been, right? Because if you've not been, and you're a big utility with stability challenges coming, you might be in trouble. Do you have series capacitors nearby? Because that's a guaranteed need for EMT studies, and there's other ones. The other question to think about when you're deciding when to do an EMT study or not is what could possibly go wrong, or what happens if I miss something? What's the worst that can happen, right? It doesn't always fit, that question doesn't always fit into the processes that we make around renewable plants. But for an engineer, sort of at the bottom of the chain, I like to think of sort of planning and operating engineers kind of at the bottom of the chain. That's where we sit. We just do the, we do the studies to try and make it work that other people have made decisions to build, right? Try and make it work. If those studies aren't done properly or are missed somehow for specific interconnections, it's very, very important. And other ones, it just practically might not be. It could be related to size or location. So we do have some metrics we can use. We talked about those last hour. SCR, ESCR, WSCR, IPSCR, CR, SCRIF, CSCR, and now NSCR, etc. And you know what all of those are, and you all know to be very careful. These aren't going to always work for you. And this is just a summary. Can you make this system on the left look like the system on the right? And if you can't, at least simple SCR metrics are probably not appropriate. We have our engineering judgment, manual review, and actually when we're working with utilities to try and decide whether to do an EMT study, this is a very, very strong tool. So a transmission map is a strong tool for deciding whether you need to do a study. One of the sort of jokes I use for people is a lot of the utilities that are trying to get into EMT studies are overwhelmed with the number of renewable connections they have, the number of models they don't have, the number of people they don't have, the skills they don't have, etc. And they want to know where do we do an EMT study? And I would usually say, what are you, like, there's going to be a specific region or a project or something that is most worrying to you. There's something that sort of keeps you up at night, or that's an actual problem that you're pretty sure is going to be a problem. You can start with that one, right? We have to start somewhere. You can start by bringing in models and bringing in checking procedures if you have people or you have the ability, but also just start with the projects that are the most intuitively scary to you, because often those are the worst problems that are coming for you. And you can look at a transmission map and see sometimes where those are. The screening metrics that we use are useful or can be useful, but sometimes they don't catch everything. And looking at a transmission map for a project can sometimes be really, really helpful, because you can see, here's an example where you would see in n-0, your short circuit ratio is 20 for this project. But if you take away an n-1 minus 1, like perhaps you take away, this line and maybe this line, that you're left with a combined short circuit ratio or composite short circuit ratio of 1.5. If you take away two sources of strength, right? And doing an n-2 anything in power flow is usually very computational intensive. Maybe it's an n-3 you need to worry about. You can probably do it and maybe catch some of these things, but you can also just look at it and quickly see at a glance that, how do I make this thing radial? Or how do I disconnect it from strength? And maybe it's 2 or 3 or 4 contingencies, and you suddenly find yourself in a really, really scary spot that might not work, right? And you can do that often by inspection quicker than you can do it with a computer program, and more reliably. Some red flags. So some things that you might automatically say, hey, I need to be really careful and think about an EMT study. One is new or untested technology. And I'm hesitant to put that one on there because everybody's so afraid of grid forming right now. But go ahead and do an EMT study. If you're really worried about grid forming and you think it might be a help in your system and you want to try one out, do it, right? Do an EMT study and see what it looks like with that specific technology and give yourself some comfort that that technology will work. If you have close proximity to series capacitors, especially when radial operation is possible, that's a guaranteed EMT study. That's not an optional EMT study. Most IBR plants, when they're connected radially to a series capacitor, will be unstable. Okay, so you really need to study that and avoid it. If you have a weak grid with serious consequences for ride-through failure. So here I'm thinking of, you know, potential for multiple plants all tripping together, or a very large plant where your ride-through failure actually will cause maybe a frequency problem or cause a major event, a voltage problem or something else. If the consequences are high for ride-through failure, you should do an EMT study. Don't forget that RMS studies, so Alex talked a lot about how, you know, ride-through is one of the key problems here. We cannot study ride-through properly with phasor domain tools. Ride-through can't be represented properly because the phase lock loops are missing, the protections are missing. All the things that can trip a plant off, other than very slow stuff, aren't in those models. Okay, so we have to use EMT to study it ride-through. Now, that doesn't mean we have to study all IBR plants in a big system model, but you probably should be looking at all new IBR plants in a small system, a SMIB system, and testing basic ride-through behavior. If you're worried about ride-through in a bigger context, like this plant or this group of plants is very, very important, you might do a system study. If your grid strength is undefinable with very high IBR penetration, you would do an EMT study. And by that, I mean, none of your SCR metrics work. There is a point when all of these SCR metrics stop working, all of them, right? Because we don't have any sort of grid strength left. We don't have any conventional grid strength left. If you have 100% renewable situation with all IBRs, what's your SCR that's uncalculable? Okay, or it's zero, whatever you like. And both are meaningless. So in that point, you really need to study it using EMT properly. And so when you look at island systems or places with very high penetration, think of Electronet in South Australia, Hawaii, Yukon, Alaska, other small areas where it's very, very high penetration. There's no other way to study that except with EMT. I mean, you can study it, but there's a chance you'll miss things. If you already have issues with instability, ride-through, or operability near an IBR plant, so if you've had an event or the system is oscillating or you're having an interaction or a problem, that's an automatic EMT study. You can't really troubleshoot these problems unless they're very slow. You can't troubleshoot them without EMT. Here's one: if the planners or operators get the heebie-jeebies, otherwise known as you'll know it when you see it, otherwise known as you trust your intuition. So you're really worried about something and you don't trust your models, it's a good time to do an EMT study, right? Because how else are you going to know? Or if your phasor domain studies, PDT models are giving you strange or unbelievable results. So if you don't trust your models, otherwise you can go to EMT. And then there's other things like classical things, lightning, TRV switching, minimum approach distances, etc., design evaluation, and then also, like I said before, when you're testing renewable plants coming in, you can do basic EMT testing as well. And those are all good reasons to do EMT. Any other questions about that? That's all I'm going to say about when to do an EMT study. There is a little bit more that could be said probably about how to use screening metrics, but those are very regional specific and screening metric specific. People have developed tools that will basically try and determine when a region is at risk for EMT or for instability and screen them out and then focus in on those areas. Some are better than others, and I'm not going to talk much more about that, but lots of discussion can be had about specifics. Okay. Question. Average cost for study. That's like if you see a manufacturer talking about StatComs, and the question from the audience is, how much does a StatCom cost? What answer do you get from that guy? Okay, so first of all, there's two questions that probably should be asked instead of just that one. One is how much does it cost? But these days, a more important question is how long does it take? Okay, so both of those questions are really, really dependent on a few factors. One is the models that are going into the study. So I can give you one example of an event where we had an event analysis. They asked us to do an event analysis, and it came in with a, we saw this on our DFRs and our PMUs. We say, please give us the models. They give us models. The models are perfect. Okay, as soon as we put them in our computers with an infinite bus and simulate that operating condition, we see exactly what we saw in the DFRs and in the PMUs. So nice. That's like, it's such a good day for a simulation engineer, right? Because now we can just like turn switches. Does that work? Oh, it's not, still unstable. Turn this switch, it's still unstable. Ooh, we fixed it, right? We turned the switch and we fixed it. The next day, we can make a recommendation. It's you just turn this, gain to this and it's fixed. In this case, turn the grid forming on and it's fixed. Okay, and then that study's basically done and you're into it for, a week of work or something.
How often does that happen?
That does not happen very often. But this is a lesson that what is really, really important, if those models are good, if they've been checked and validated against actual system models, the studies go so much better. If you start with bad models, either you don't see what you're supposed to, or the models are not behaving properly, or you're going back and forth, or you find out that it wasn't the as-lefts or whatever. So that's a big variable on cost and schedule and actually study effectiveness. The other one is, how difficult is the problem to solve? Sometimes it's a very simple problem. It's just a control change, or it's something else. But if you're trying to get right close to the bleeding edge of what's possible in that region, how much wind can I put in this location is a very expensive question. Okay, if you're asking me, what is the edge of stability? Can I do 150 or can I do 175 in this location? That's an expensive question because you're right at the bleeding edge of stability. Everything is touchy, everything is sketchy, and the models are touchy, and you have to just fight with the thing the whole time. So that's more of an expensive question. The studies are not that hard for trained people to do. The difficult part these days is getting good models. So that will drive your schedule and actually drive your cost too. So that's all I'll say about that. Yeah.
Building like a semi-activated model. If you do the activation like different, get like different results. Or something that's implemented, say like adding intermediate something, get you like something results or different results, or if you use like a different portion compiler, like set up the same case in like different machines, like deal different results. How do you make it done?
Yeah, that's a very good question. Let me think about how to answer that. I think in the wide spectrum of EMT studies, we don't get to see true validation of the studies that we do very often. Those are like data points for us when they happen. So occasionally you'll see an SSCI event, or you'll see one of these events like what I just described, or you'll see a fault that happens in a model that we've been working in a system for a long time, and we get to see the DFR recordings. and you get to see like a validation. And usually they're not perfect. There's some problem, but often they're not bad. And I think the confidence that you get from an EMT study is derived from a few things. One is the quality of the models that you're putting in, and you usually have a good sense for that. So if you're getting bad models in, a simulation engineer usually has a good idea that they're not very good, and already is starting to add disclaimers in their head about the study, right? Like you have models coming in from developers or from utilities. You can see that they look like default parameters. They look like something that's not correct. You're in your mind, you're degrading the value of your study. You're already imagining that this is going to need a disclaimer. Other times you get really confidence-inspiring models, or models you've worked with a lot, or OEMs or developers you've worked with a lot that you know have good processes. You have faith in their processes and in your own quality control processes that you kind of trust all the pieces of your model. And then you start to feel more confident in the model. And those are the ones that you get those spot benchmarks throughout your sort of study career, where you can see, yeah, this one we were quite a bit out on this one. This one was pretty good. This one was pretty good. This was pretty good. And you try and learn from that and improve your modeling processes. So you have to trust two things. One is the models coming in and be confident with those. And the other one is in your study and model quality control processes, which is, how do you make your network equivalence all the time? How do you make what are your input base case, checks looking like? And there's all kinds of quality control things that study engineers can use to at least make sure that all of the things we can compare against are matching and correct, and you get the maximum amount of sort of confidence. But you always know, as somebody said the other day, that it's still a model. And in the end of the day, the real system is going to have differences that might cause you to be out. The other little things like, compiler differences and those kind of things, those are like, they're common, but they're kind of anomalous. You already know that there's something wrong. As soon as you're getting different results from different computers or different compilers or sensitivities to network equivalence and things like that, you already have a sense that there's a problem or a sensitivity in your study process that is that should give you pause, and you need to sort of sort that out and figure out how to add confidence in that area before you continue on. Other than that, you're adding disclaimers back into your report that says might be wrong. So one of the things that we hate the most, I'll just give you this, is from like a study consulting shop. Especially nowadays when all the study consultants are busy, is when we get sort of instructed to go ahead with the study anyway. So the first thing we do is we look at the models and we say, these models are garbage. They're wrong. And they say, we need to go ahead. We need to get this checkbox done for our study, do the EMT study, because the utility is asking for the EMT study. And we say, but the answer is going to be wrong. Like, we don't care. Go ahead and do the EMT study because we need an EMT study. That's like soul crushing, right? Because you're doing a huge amount of detailed work and you know you're wasting your time. And any result that you're getting is going to be, at best, an estimate of what might happen. So, but that is the world we live in right now. Sometimes you have to do that, but it's really not good. And the study consultants will usually disclaim it.
Yeah, but it's really easy to like fall into the mindset of these are all wrong, all my studies are wrong. But every once in a while, you get one with a real validation, and you see it work in real life, and then you get that confidence back. But everything Andrew described is like what years and years of engineering judgment that you learn by mapping. Like, oh, this was a good process, and then I had an event and it matched, so now I know what good looks like. And you just kind of build it over time. And the slides from a long time ago I showed briefly, the very last slide of that was one of those good examples where the exact same contingency happened like a month later. In the real plan, we put it on top of the EMT plot, and it was the exact same. We actually put it on top of the phasor domain plot, and it was the exact same. But that was one of the OEM involved, really high quality consultant involved, really good transmission service operator wanting to get involved as well. And that was like a perfect storm. And then those are the results you get if everyone's doing best practice together. And that's when it gets frustrating when someone's not doing best practice. Then you get that kind of soul crushing piece. But it's not to say that every study is going to be wrong always. I mean, it depends on what wrong means. But you can, with good processes and good quality consultants who know what they're doing and saying like this is wrong or not, you can actually see real events match exactly what you tuned it for.
Yeah.
exactly control like model quality. You're right. So if you're not trust the model, you're working with definitely that's going to be a problem. But all these uncertainties like embedded with the EMT simulations, then how you decide? So for example, like different ways you aggregate.
Yep. 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 I think I understand your question.
Why?
So,
Get like different results. Now you need to make a decision.
right. And that's a good question. And I think that's part of the process as well of experience is that that bothers the simulation engineer doing it as well, by the way. And when I'm working with junior engineers, best practices can be bent. We can change the rules for these studies, and we do all the time, depending on what you've learned from other studies. So another example would be, how are you going to model the transmission lines? Are you going to use frequency-dependent transmission lines or not? And how far do you go back? Are you going to model transformer saturation or not? Are you going to aggregate or not? All of these choices you have to make in EMT simulation to try and decide how much detail do I really need? Because in EMT, there's a bottomless pit of detail, right? And it's very easy, especially for new EMT study engineers, to not know where to stop with adding detail and this is where some of this push for disaggregated models is, what if we're missing something? You need to do sensitivity studies, and sometimes we build those right into the study. So you say, I'm not sure whether I needed to, like a good example is transmission line modeling, because you have sometimes very, very complex rights of way coming into a station. You have mutual coupling between different lines, sometimes multiple circuits on a tower, and all of that changes the sequence impedances of the system, changes the mutual coupling and the induced voltages on one phase from the other. All of that stuff gets overwhelming, and the lines can be very, very difficult to model. It can take you a week to model a right of way. Do you need to do that? And so you have to get some senior engineers in to look at it and then decide, okay, that could make a difference. Maybe it makes 5% difference in this type of transient. We're going to make a statistical call. We're going to just make a judgment call on the probability of that mattering at all, and then throw it out, right? And that's hard. Every time is a judgment call. It's the same thing with aggregated models. It's the same thing with all of these other things. For example, if you're doing anything that relates to transients, how much of the detailed IBRs do you need to model? Because you're worried about such a short time, you have to decide how quickly are all of those IBR plants going to come in and actually impact your transient overvoltage. And if you model everything, it's going to be a 6-month project. If you model nothing, it's going to be a 1-week project. And it's going to impact the transient a little bit. So what should you do? Is a judgment call, right? You have to get your good brains into the office and think about it and make those calls. And everything you do impacts the overall sharpness of your study, but hopefully you're getting the point of the study and you're getting a good statistical probable outcome. There's no short answer to your question, I think, except for sensitivity studies, experience, and also not sweating the details too much with EMT. You can do a lot of sensitivity studies that show you, yeah, you can add all that detail and it'll change the result by just a really small amount. So let's not do that. Let's focus on the things that can really, really change the result, like the code and the inverter model, for example. And just focus your attention to try and bring the study as close as you can to a useful thing in a short amount of time. I don't know. Unsatisfying. I told you you'd be unsatisfied at the end, but okay, let's move on. It's a good question, Amir. Okay, I just have a couple of slides on sort of a design of a weak system study. This is an old slide and I don't really love it, but let's go through it really quickly. General steps: we want to develop and publish the criteria on model quality. So this is on the back end. We need to have the model quality criteria. The models come in and the quality assurance is done right away to make sure that the models are good. So you have to ask for the models, you have to ask for the right models, and you have to check that you got what you asked for. That's the basic step that all of these studies are going to rely on. So everybody should be doing that for all your IBR models, right? That's the basics. Then when you're deciding you're going to do a study, you ensure that your input design cases are as good as possible. So that means that your power flow and transient stability results are done and they hopefully make sense. So you figured out If there's a voltage collapse scenario, you find that in power flow or in transient stability, not in EMT. Okay, EMT is going to find it, but with a lot more work. That's what those tools are designed for. Power flow and transient stability are still useful tools to find basic problems in power systems. So solve all the basic stuff and then go to EMT. Then you're going to develop study parameters, you know, in conjunction with everybody. Everybody's going to agree on what to do with this study, and you're going to try and rein it in, right? When you're doing EMT studies, you really want to focus your effort. We can't just study everything. This is the problem with new EMT study engineers is let's just study everything because we don't know what the worst case is. Figure out what your worst case is as much as you can. Narrow it down to, let's say, make yourself a target of 5 faults that you want to study. Okay, we're not doing thousands of faults anymore like you can do in transient stability. You want to narrow it down. You want to agree on what you are doing the study for. Okay, you're not doing EMT studies because EMT studies, right? We're doing it because we're interested in ride through for this plant in this area is going to be a problem, or you're interested in, you know, SSCI damping in this area, or you're interested in something specific, control stability in this ultra weak system. You're trying to solve that problem. And this isn't just true for EMT studies. This is generally studies. We want to have a reason for the studies and a specific goal or question we want answered out of that study, right? Put that in your executive summary. We're going to negotiate the size of the study area in EMT. And this is a big issue because we have to decide how big is the system going to be, how far back do we want to go. And I think the course in December will talk about this, some concepts around how to choose that study area a little bit more. Negotiate the outage list, and like I said, you want to minimize that outage list. Agree on what you're going to look at, and this is related to the first one, which is what are you trying to answer? Remember that in EMT, you can quickly generate yourself thousands and thousands of traces that are very, very wiggly. Okay, there's a lot of things you can look at, and what are you actually interested in? What are you going to focus on? So decide ahead of time, what are you going to look at? What are you going to plot against what? And decide what you're going to look at. And then decide on what's a pass and what's a fail. How are you going to judge that? And that's sometimes hard to tell early on. Here's a little bit of what we do is we organize our data into libraries, and I'll show you another slide that says this is just basically data organization problems that lets us maintain and continue to develop models quickly. We organize the case for parallel processing, load balancing, port mapping, and all of this. And this is now moving towards system studies and not just like individual model checking, like you are all planning on doing now from now on. You're going to develop automation and control for faults and outages, monitoring of critical quantities, pass-fail analysis, and plotting. And this is because, again, there's so much to look at. You really want to have some help from automated scripts. So most consultants doing this will be automating these studies to some extent, and then you mitigate and iterate as needed, okay? This is the rough flow that we're talking about, and on the top left, you can see many phasor domain runs should be done, power flow studies should be done to identify the worst cases and understand the wide area dynamics. So those are what you're doing first to try and narrow down the problem. You may also do other screening things to figure this out. All of those studies basically are going to end up sort of producing your base cases that you're using for input into the EMT process. You also have all of your verified, so we've got our PSSC studies are done. We have all of our verified IBR models. So these are all the work that everyone's doing to make sure that the models are correct. The stuff we did yesterday, all the NERC recommended practices, there's lots of automated tools. I think other folks are writing now, even for sale, to help you do this. The outcome is a model that you can trust of the individual plant. So that's an input. You need to model all of your system components. So transmission lines, transformers, synchronous machines, HVDC, faults, monitoring, all of that. These models all go into what I was talking about. Libraries are basically organized into sort of readable libraries for our other tools. We have study area selection, which basically is the engineering judgment part, where you get the most senior engineers in your shop to look at a transmission map and think about the problem and come out with what are we actually doing here, choosing the boundaries, choosing the faults. And then you come out with a bus and a contingency list. We have our solved power flow and dynamics. And then we put it into a tool that basically says, take that area, take all of this data, produce an EMT model. So the output of this tool is an EMT model. We hook that into parallelization, automation scripts, and so on, and then we run it. So that's how phasor domain and EMT are integrated. So if you need to change the size of the system area, or you need to change the case list and so on, that's all done on the back end over here. So these EMT IBR models can be referring to repositories or GitHub organized libraries that can just pull the most recent ones. So this has evolved quite a lot. I expect in the future this will also be said it stopped sharing for a sec. I expect that this will be abstracted even further so that hopefully in the future you won't need to be an EMT expert. You can sort of specify your parameters for the study and get the output. Quick note on co-simulation, because we just get this question a lot. There is co-simulation modules that allow you to run EMT and phasor domain tools together. And, you know, on the surface, this sounds like a really great thing. This will help us use smaller models. It sort of bridges the gap. And a lot of folks glom onto that idea as, well, let's explore that. And I just want to quickly talk about when you might use it and when you might not. So first of all, if you want to do co-simulation with phasor domain and EMT, you have to be expert in both tools. Okay, so don't forget that. We haven't made things easier for ourselves. Now you have to be, if you're using, for example, PSSE and a PSCAD or something, you need to be an expert in both those tools' dynamic capabilities, as well as the expert in the interface between them. So this is not a sort of a bridge technology. This is advanced EMT, okay? But there are uses for it. So if there are regions where you have a high path flow through your study area and you don't want to stick an infinite source equivalent on the boundaries, because when you take a line outage in the middle, all your angles are going to get shifted around, and now they're going to be wrong. Because don't forget, when you move to EMT and you put fixed boundary equivalents all around the edges, those boundary equivalents lock the phase angle and the voltage. And so you end up with no way to move that anymore. That becomes fixed, and all your angles inside are relative to those angles. In the real system, if you change something in your study area, those things change too, right? Everything, the whole system moves their angles. And so that can be important if you're interested in post-fault angular effects. So post-fault flows being important. They're not always important, but if they happen to be important, that's a good example for when you might use these. If you have inter-area machine dynamics, so you have one area, like for example the Panhandle in Texas, and then there's a mode that interacts with somewhere in the middle of ERCOT's system that it can move against each other, then you can't represent that with fixed boundary equivalence. Again, you might need to use co-simulation. But keep in mind, you would only do that if you care about that oscillation, right? Most of the time you're doing like fault studies or something in the region, you're interested in ride through or control stability or something in this region. If you add a 0.5 hertz slow oscillation on top of that, it doesn't actually change any of the ride through stuff. That's a separate problem. That's an inter-area oscillation problem. If you don't care about the inter-area oscillation problem right now, then don't waste your time looking for it, right? Or adding it to your simulation. It's not going to change anything, so don't worry about it. But if you care, you can do that with co-simulation. You can use it to glue different tools together. Okay, so if you have a really good model of an HVDC link in a phaser domain tool, and you want to interface it with a large phaser domain tool of a different version or a different system, and then you have another EMT model that you want to plug in over here, and you just don't have models in all the tools and all the versions. It can be like a tool glue that can connect all of them together. And the last one I'll give you is just, and this is probably the most we've used it the most. If you don't know what you don't know and you're worried about it, and you just want to try it, in that case, you would do a sensitivity, hopefully, and decide how much does this matter. So one example is we had a long radial case where we're studying, weak system series capacitor issues over here, and there was a connection bus with a bunch of synchronous machines over here. And my feeling was, this is really strong. Nothing we do over here is going to matter over here. But the customer didn't believe me. And so they're like, I think you need to model all of that stuff too in EMT. And I'm like, that's going to make it really long. Let's try this rather. Let's add a co-simulation, see if it makes a difference. And if it doesn't, we'll just fix it there. And the customer was okay with that. And then you can see, sort of validate where the boundary of your EMT study should be, right? Give you some confidence. Alternatives to co-simulation, of course, you can just make a bigger EMT model, and sometimes that's the best answer because you have enough processing power. It's not that big anyway. Just model a bit more and capture those machine dynamics. You can also just pick machines and put them into the model through the appropriate impedance networks. And just always remember, that you need to be thinking about the answer you're trying to get. If that particular dynamic element, it's a dynamic element, it's going to move and it's going to change what you're looking at, but is it going to change it in a meaningful way or something that could possibly impact your answer? And if the answer is no, leave it out and make your model simpler, right? Okay, any questions on that? I'm going to go to grid forming last, but not least. Yeah. Yeah. Yeah, that's a good question. And I think this is something that's a live discussion, and it's also mixed with commercial discussions in the EMT tool space. There's kind of a thing right now where either study consultants or tool developers are kind of getting braggy about how big their models are getting. Like we modeled this big of a system, this many buses. We modeled our entire province, or we modeled this entire state, or whatever in EMT because we're good citizens, and a little bit of virtue signaling maybe on there. And I feel like it's not that helpful from a problem solving standpoint. Most of the time we don't need huge models. In fact, very rarely, if ever, do we need really huge models. We might get there one day when it's easy and when it's cheap in terms of computation and human resources. But most of the time, I would say 95% of the time, when we're looking at these models, you want to stop your model where it stops mattering or where it stops impacting you and focus on your problem. Because if you try and model everything, first of all, you get a very big, heavy, complicated, buggy model that's hard to maintain. The second thing is, now before you had 2,000 traces to look at, now you have 100,000 things to look at. And what are you going to look at? So what are you going to do with all that data that you generated? Now you've modeled all of those wind farms. You can try and pull out automated things, but it becomes very, very heavy. And this is a little bit of my opinion. Our approach is not to do that. We prefer to basically every single time choose how big your model should be based on what you're looking for. And then also think about how big our computers are and how many people we have and how much time we have, and really focus on what question you're answering. It's a missing piece right now in that discussion. We do model some very large systems. We model, if you're looking at, in the West, they're putting in fixed series capacitor after fixed series capacitor and connecting all of these different systems with brand new fixed series capacitor lines with generators all over. The only way to study that and get all this, the modes, is to model the whole thing in EMT. Fine. There's a specific thing we're worried about. We're worried about getting those, you know, complicated frequencies right and getting all the series capacitors right. Or in Hawaii, we're worried about all of the DERs tripping at the same time and seeing what happens to the overall frequency when all the DERs don't come back. And so we need to model all 200 generators in that case, because there's no other way to really understand what's going to happen to the frequency. Fine. But if you're looking at a renewable plant, and again, I don't want to get too much into how to select those boundaries. We'll do that in the December course. But there are principles you can use to say, if something changes over here on the other side of this big transmission line, how much can that change this renewable plant that I'm interested in? So if I'm interested in this ride through of this plant, the voltage is important at the terminals. If I change that other plant far away by 100 megawatts, and it's just going up and down by 100 megawatts, but it has to come through this big transmission system in the meantime, by the time it gets to me, the voltage is moving by 0.5 per unit. There's no way that ripple is going to impact ride through. So that means I can stop at that boundary and you know, stop that model there and focus over here, right? So there's a lot of sort of good practice in model boundary selection that can be done to really keep your speed up. If you want to do the big models, go for it. And sometimes there's a need for it, but I think it's useful to keep it lean. But that's my approach.
If I could add something you said is one of the things that's kind of dangerous as a mindset, which was, do we need to go to EMT to study the IBRs and what they're doing? Which is a very common mindset, because EMT is this newer thing and this shiny thing, and it has all the accuracy. So a lot of folks say, well, we have to use EMTs for all IBRs all the time. There are problems with positive sequence modeling now, but there's a lot of work. There's a lot more work you can do in positive sequence to make those studies much better and capture a lot of things that you don't need EMT for. Like EMT, like Andrew said, is a special application, really necessary, really complex, detailed controls, things like that. You can do a lot more. We're here with phasor domain right now, positive sequence. We can be here, and EMT is probably up here, but we can close this gap, huge gap. So a lot of the things that a lot of people just jump to, oh, we need detailed models for EMT. We need all this real code for EMT. You can do that same thing in phasor domain, but that gets left out as everyone jumps to the new shiny thing. But the fact of the matter is, based on all the things Andrew said today, how to pick and how difficult it is and computationally intensive, phasor domain modeling isn't going away. And the fact of the matter is, phasor domain modeling is probably going to be 95% of most of the modeling, 90% of most of the modeling in a lot of the planning cases and interconnection planning cases now. So we need to just kind of apply those things back to phasor domain as well, because you can do a lot. There's a massive gap between the best phasor domain models and the worst phasor domain models, even amongst the major OEMs. So, which is really important to keep in mind, that phasor domain positive sequence modeling isn't going away. But the things that sound cool that we agreed to for EMT, you can still do in those tools. So it needs both.
That said, the number of cases that deserve an EMT study far outpace now the number of sort of capability to do it. So yeah, anyway. Okay, grid forming. I'm going to stop at about 4:30, whether we're done or not. We can sort of wrap up. The main thing I want to get through with grid forming is just helping you all understand what this term means. Okay, so everybody so far has been very hand-waving in this course, including me, to just say grid forming is great. We should all do grid forming, turn on the grid forming. Grid forming solves weak system problems. Grid forming is this and that. So what is actually grid forming? What are we talking about? So I put some definitions down here for you, which you don't have to read, and I'm not going to read. But basically, what we're talking about is grid following is right now everything. So it's current generation wind turbines, PV, DER, BESS, LCC HVDC, most VSC HVDC, current generation STATCOMs, actually I should say last generation STATCOMs, and SVCs. Okay? What is grid following or grid forming? Grid forming is the new stuff. And the way that we're going to specify it, all of this language is here. You know, we wrote a long time ago, and it's similar stuff is in a lot of definitions. But the way I would describe it in very short form, and I'll illustrate with some pictures, is the capability of a plant to hold its internal voltage phasor constant. So the magnitude and phase constant in the short time after something changes in the system. Just like a synchronous machine does, that quality of not moving when the system is moving, resisting the change of the system, is what grid forming is. And it's a very short time period afterwards. So let's see what that looks like. So here's our test system. So what we have here is a battery, which could be grid forming or grid following. And then we have a terminal bus, and then a transformer, and then a common station bus here. And then we have a load. And then I have a generator, synchronous generator with a breaker, and then a connection to an external grid with load and other things. Okay, this is the test system we're going to use. Grid forming, if we're just thinking about angle now. So I said voltage phasor, which means magnitude and angle. We're just going to think just about the angle for now, okay? So a grid forming battery is going to hold V1's angle, so theta 1, constant in the transient period, so T1 plus. So we're going to make a transient in the system by opening this generator breaker. So generator breaker is going to open at T1, and T1 plus is the time we're interested in. So right after that T1, theta 1 is going to be held constant in grid forming mode. In grid following mode, we're going to abandon that control philosophy and hold P1 constant. Okay, those are the two differences, and just in that period right after the fault. And that's the difference between grid forming and grid following. So what does it look like? So now on the top left hand, I'm going to just do something temporarily. I'm going to open up and get my highlighter back. I'm going to open up this breaker over here. Okay, so we're going to take away the system. So now we're basically a microgrid. We're an islanded system, and we're going to do this T1 thing. So what's going to happen to our grid in grid following? So on the left side here, we have our grid following quantities. If we have our active power is going along here, grid following, remember our control objective is to maintain constant power. P1 is going to be constant, and so it's going to try and hold this constant. Now in reality, in that case, we have a very, very low short circuit ratio, right? And so a grid following controller can't really hold stable in that situation. We're just going to kind of imagine that it could, and it's trying to. In reality, it's going to be, you know, this yellow thing. It's going to oscillate and then trip. But what it's trying to do is hold its power constant. Now, notice right at that T1 moment, it's not exactly constant. It's got a little blip there. And the reason for that is a pure grid following device is trying to hold its power 1 or its P1 constant, but how does it do that? It does that by tracking the phase angle of the system and using its very, very fast PLL to track the phase angle. But it's a very, very fast PLL, but it's not an instantaneous PLL, right? The PLL still has a bit of work to do, and so it takes a moment, and in that moment, it's not perfect, and you get a little bump. So what happens here is phase 1, theta 1 and theta 2 track each other. So theta 1, using that PLL, tracks theta 2 so that this distance is constant. Drawing arrows with a highlighter. Okay, so grid forming, what are we going to do? Now we're going to hold theta 1 constant down here. So that is easy to do. That's not controlling anything. That's just not doing anything with your phase angle. And so it just stays constant. And what will happen now is we get a difference. The theta before and the theta after is now different. And what does that mean from our tattoo equation? Power changes instantaneously, right? So the power has to take a step, because we've changed the angle between those two. So when the angle took a step on the bus, the power took a step instantaneously. We can call that an inertial response. And since there's nothing else in the system to synchronize to, this is now forming the grid and makes up the difference in the load. Okay, great. Any questions? Make sense? We're going to add more stuff to it, but okay. Now let's reconnect our island. So now we've got our island is breaker closed again. We're synchronized with the system. So now we're grid connected. We're going to do the same thing. So we can see in our grid following device, we have the same thing, basically. We're tracking the power, we're trying to produce constant power, and so we do. The theta and theta 1 and theta 2 are tracking each other, or the theta 1 is tracking theta 2, and so it matches and that keeps the angle constant. The grid forming battery now, though, we've had to add some kind of a synchronization control to it. So either we're doing virtual synchronous machine, or we're doing a droop control, or we're doing, like we talked about yesterday, maybe a slow phase lock loop controller that brings it back into synchronism. And so nothing is going to change in this first moment. Remember, T1 plus, theta doesn't change, but right away it's going to start changing. In that period, before it has changed, we're still going to get that change in active power because we've still stepped the angle between the two. So we have to get that change in power. So we're going to see that power step, and then as we reduce the angle, so we're going to use our synchronization controls, whatever those are, to bring this angle back in line so that we get the power order that we wanted, right? Now, how we get there to the transient power back down to the synchronized power is down to the specific GFM controls and even GFL controls. You can add in GFL controls, do what you want with the power afterwards. But in this moment, that's grid forming. So that little blue circled thing is what we're calling the grid forming response, or the inertial response, okay? And that's basically grid forming. If you take nothing else out of this course, that's how grid forming works. Everything else is just going to be details, how to limit current, how to do different types of controls afterwards and deriving benefit and all of that. But if you want to know what people mean by grid forming, whether it's in an island or not, microgrid or not, synchronized, that's what grid forming is. So no more discussion about nobody even knows what they mean by grid forming, right? We know. It's this. That's all it is. Okay. Yes. Right. Yeah. The question is about headroom. We'll talk about that in a sec. So there's definitely stuff we're going to have to talk about here in addition to this, but this is the basic concept of grid forming. So we're going to talk about headroom next, I think. Almost. First of all, we've added power control and grid synchronization, but we can also add frequency droop control, right? Because most of these generators have some power frequency droop. If you're in grid following, you end up with, again, we track the system angle, and then we add, since the frequency has changed, we add a little bit of droop to it, and we end up with an error in the, oops, wrong color. We end up with an error in the power from before because the frequencies changed. So we get some difference in angle down here. Nothing changes with grid forming. In fact, everything we're asking for from grid following, like Alex said yesterday, we basically are keeping all of those services. So frequency control, frequency droop control, in steady state, voltage control, all of the things that we want ride through from grid following, we also want from grid forming. So we're going to get the same steady state error over here, but the difference is going to be, again, what happens in the short time afterwards. So that short period, that inertial response, or that automatic physical response, is what's giving us our small signal stability. It's basically resisting changes in the system and not allowing the controls to move quickly. Okay, so that's what gives it that very, very stable behavior in weak systems. Now, what happens if we don't have the room to go up in power? So the natural response of the system is to go up in power, but what if we're already at max power? We can't go there, right? So if the battery runs out of headroom, or if you hit a current limit in the battery, then the controls have to do something. You can't get blood out of a stone, and so they will have to limit it. And that is where the response starts to vary. So there's different ways of limiting current in grid forming controllers. And we don't have time in this course to do it, but there are a number of functions that methods we can use to limit current. That's a research topic a lot of people are working on. And it turns out to be a pretty important one for challenging systems. So if you're in Hawaii, you're the only grid forming plant in existence, and they're putting horrible faults on the system that last forever and they have phase angles included, you need to really take care of this problem, okay? And if you look at some of the tests that we're going to talk about later, we focus particularly on how current limiting is done to make sure that you do it in a stable way and you don't cause more problems than you're solving. So this is the kind of thing, current limiting can be tested in isolation the same way we test IBRs in a whole set of things for fault ride through and frequency response and all those things. We can test these grid forming qualities in tests as well to make sure that you deal with fault ride through properly, that you limit your current in a graceful way. Okay. So how you do it is going to be down to the controls, and that's where a lot of the innovation is happening in grid forming, and where there's a lot of room probably still for improvement. But I will say that most of the major manufacturers who are developing grid forming controls have been focusing on this. It's the obvious problem to focus on, and they're pretty good at it. Just maybe one more anecdote on that. In Hawaii, where a lot of the first grid forming studies were done and a lot of the manufacturers who are currently making grid forming batteries were first tested, those faults are truly nasty. So what happens is the fault goes low, the voltage goes low, it stays low because they may have delayed clearing or problems with remote breakers opening. And while it's low, the frequency is crashing. Okay, so your voltage is bad and your frequency is moving. And so when you try and come out of that fault, the grid forming device at some point, not only does it has to limit current during the fault, when it comes back out of the fault, it needs to be very careful not to resist coming out of that fault because it wants to resist change, and it has to come back into a reasonable phase angle without causing a big transient. It's very hard to do, and what happened is they ended up doing a lot of tuning on their controls in that environment and against those tests to try and make that fault ride through robust. When you move to mainland US and you're in stronger systems and you put a fault on the system, they seem relatively trivial for these plants to ride through at this point. So a lot of them have been working really hard on really challenging systems. Seems to be helping them in the good systems.
Also, just in addition to a technical problem, a regulatory problem as well. Like how do you make a performance requirement for when you hit a current limit when all of the responses are going to vary, and what do you do? So just, I don't have any anecdotes or examples, but it's a problem we need to think about.
Yeah, and I think you can do you can take a balanced approach to that. Like I don't recommend that most utilities use HECO's grid forming tests, at least not all of them, because those can actually influence sort of the optimal behavior in stronger systems. So most utilities, you want to have tests for grid forming that are relatively representative of what's going to actually happen in your system so that those systems can be tuned reasonably for your system. What can go wrong? Actually, this is an old slide, and this is a little bit of a funny slide. The first time we did a major grid forming study in Hawaii, it was basically 100% renewables, and we had grid forming, and we saw a very slow oscillation in active power across the whole island. And it seemed to be coming from the grid forming resources, the generator resources. And so I made this slide that said, this might be an inter-machine mode or an inter-GFM mode or an undamped oscillation, kind of a mini inter-area oscillation. Everyone was like, oh yeah, that could happen. Not sure exactly what's going on there. And we all thought ourselves very, forward thinking, and, we need to watch out for this. And maybe we do, honestly, but it turned out that we had left a infinite synchronous, a tiny little DER had been left as an infinite voltage source with a low impedance inside the system model, in the EMT model. And that basically was holding the angle constant artificially and causing the whole island to slip against that one. So it was a pure bug in the system model, but very hard to find. And it caused this massive oscillation across the whole island because of this little source. So just a complete error in the system model. Not that this couldn't happen, but in this case, it was a bit of a red herring. Additional reminders about GFM. We do need energy and current headroom to derive some of the benefits, not all of them. Current and energy headroom are not needed. Generally, in the small signal space, you do get a bit of stability. It can operate in weak systems. There are lots of ways to implement the controls, virtual synchronous machine, Droop, and other, like Alex was showing. And a lot can be done to shape those needs. And it's not a good idea. I think there was a short and ill-advised effort to make a standard on this, basically to say how everyone should do their VSM controls. Maybe it's a good idea, but I don't think so. I think it's too early to do that. And what's turned out to happen is that depending on how different areas are asking for inertia or asking for fault ride-through or different characteristics from the grid forming, the manufacturers are making their controls very flexible. Now, that's a good thing and a bad thing. We like a single simple set of parameters that work, but they can actually do quite a lot if you need them to. For resources with energy and current headroom, like batteries, the hardware is generally similar. We talked about that yesterday. And generally, all of the things that GFL can do should be expected from GFM, with a few not very important exceptions. Okay. One exception, for example, would be if you are doing a grid forming StatCom, just a conventional StatCom, not an e-StatCom. Most of the StatComs now are being specified as grid forming, or a lot of them are. What happens there is we used to, for a StatCom, specify response time for voltage response. So if the voltage step happens, how quickly does your reactive power get injected? And it was kind of annoying because the StatCom manufacturers, or the people making the specs, would be like, we want fast, it's a StatCom. And so they would specify something right at the edge of the capability of a StatCom, like 50 milliseconds or something. And the StatCom vendors would be on it. They would make it fast, 50 milliseconds, or 50 milliseconds. And then all through their controls, they would have special controls to keep it stable at 50 milliseconds. And they would have adaptive gains that would keep their gains approximately right to give you that response time for any system strength. And did we really need 50 milliseconds? No, most of the time not. But those carried forward into grid forming specs. Now we have a grid forming controller. What they're doing is they're saying, let's just do the grid forming response. So if you have a fault, it's instant. But then we'll make an outer loop voltage control, which is a little slower. So you get a different shape response, and you don't get that 50 millisecond, hyper-tuned PI controller response, but you get what you need, right? So this is a bit of an adjustment in thinking that I think we have to make a little bit about grid forming resources. And that's the same for batteries. If you do a step change in the system, you're going to get a spike out of the device. It's always going to happen. And sometimes you see that on a simulation trace, and you say, I don't like that spike. Why is it spiking? I didn't want it to spike, or I didn't want it to oscillate in that way. It's resisting the system in the way that it's designed. It's not hurting the system. It's resisting the change. And so you have to get used to seeing those new types of behaviors from the devices. Okay, applications. So we're calling this the killer app. I made this for Unify a long time ago. Short circuit ratio is going down in the system. If we're using short circuit ratio, I got a slide down here, becoming less value, don't use them. Short circuit MVA is being provided by synchronous machines. And now you can say also grid forming IBRs and grid forming HVDC. So that gets added into the numerator of your equation. So like we were talking about at the break, if you just want to generally make your system stronger, adding grid forming into the resource mix, no matter how you're calculating short circuit level or system strength, it's helping, right? It's increasing the short circuit strength. And taking it away from the bottom, because now a resource that was grid following and sucking on your system strength is now on the top of the equation. So a couple of sample sort of applications. And there was a study done for ESIG a while back that actually had some really nice real world examples on this. You can go looking for in the ESIG library. It's called Benefits, GFM Benefits, I think it's called, something like that. But in this example, we studied a grid following IBR, and this is the same exact scenario that we were looking at in our mode cycling example, right? We have two paths out and we lose one path. We're left constrained on the other path. And so what the grid forming battery was intended to do was to transiently both strengthen the system, so it gives the system more strength. It's like adding a grid forming battery down on the bottom, and also it was controlled to change its power order when that happened, and so it could transiently move power in and offload the flow from this plant. And this was real equipment that was studied. It was unstable before and stable after. Power system damping. So we talked a lot about this for SSCI, and this is possibly one of the biggest value adds in the short term for renewable plants going into series compensated areas. And a number of developers are building grid forming batteries in absence of any requirements, just because this is unlocking capacity for series capacitor constrained regions. So if you have an SSCI damping problem or an SSR problem, you can add grid forming batteries, and what they have is a very strongly positive damping characteristic in the subsynchronous region. So they basically cancel out any bad negative damping you're adding with your IBRs. Okay, so this is just a function of being grid forming. If you add special tuning, you can actually tune the grid forming battery to provide extra strong. You can put a spike on at 15 hertz or 20 hertz or whatever your problematic mode is. You can actually add extra damping at that mode with some tuning. So this is a powerful tool for mitigating SSCI. There's almost no other mitigation for SSCI. This is just another example. This is a test system where we have a grid forming inverter and a wind plant and a series compensated line. You can just see that the instability grows as you get to 350 megawatts with no grid forming battery. If you add a very small grid forming battery, so this is 50 megawatt grid forming battery, you can just about double the throughput of the wind plant, and then it eventually goes unstable. If you add extra tuning, you can bring it all the way up to 550 megawatts or something. This is one that's interesting for island systems or small systems with frequency problems. This is coming from Hawaii. So looking at the frequency here, on the right side, you can see an event where they have a lot of generation being, what's actually not happening is generation being lost. It's a fault that causes the DER all to block. So the DER all blocks for 30 seconds or half a second to maybe a second. And in that period, this is the DER doing this on the left. So the DER goes to 0 and ramps up over half a second or a second. In that period, the penetration of the DER before the fault was nearly 50% of their entire load. And so the frequency goes down very fast and very far. You can see it going all the way to almost 58 hertz here. And when it hits those levels, the load shedding starts, right? So this is the load shedding on the top here. These are different loads being shed. So we can fix that with different devices. If you have a GFL on top left, GFL with no FFR, you basically get nothing. You might even get momentary cessation, so you get nothing. If you put a synchronous condenser in, you get the right initial response, right? You get the grid forming response from the machine, but then it's a machine, so it has to swing. So you get the active power energy there, and then it swings down. If you have a synchronous machine with FFR, again, you get that nice punch of energy, but then it takes it back and then slowly gives you the energy over here as your synchronous machines governor kicks in and you get the FFR response. With grid following in FFR, you can finally get some response over here, but this tends to be after the half-second period, and you could see how fast the frequency is falling. So really the only solution to that frequency problem is something that's fast enough to be grid following. Grid forming is fast enough to give you that energy, but also special controls that hold it high, right? So either droop controls or some kind of mix of droop controls and inertial controls that can give you that energy gap. So this is really the only solution in Hawaii to keep their frequency from dropping low. I had another slide in here, but I didn't put it in. Basically, another thing you can think of it as, if you're using it with HVDC, there's a number of HVDC grid forming plants in the world. HVDC, if you put you can put grid forming on one side of an HVDC link, and that essentially strengthens that side at the expense of the other side. So it will move current in and out of the weak side to strengthen it, but the other side has to give you that current. So you can think of an HVDC line with grid forming as a pipeline for grid strength, kind of. So you can move system strength from one region to another through HVDC with grid forming. So it's another application. Following apply to all resources. So we talked about this a little bit. Has to be dispatchable, steady state voltage control, dynamic reactive power, active power frequency control, ride through, fault current negative sequence. Actually, negative sequence is a natural byproduct, again, of being a voltage source. And what we're seeing is that as you retire synchronous machines, those things have been absorbing negative sequence in the system for a long time. As we turn them off and just replace them with grid following resources, our unbalance in the system is rising a lot. Okay, so all of that natural imbalance that we have in the system from unbalanced loads, from untransposed transmission lines, all of that is coming home to roost because all of the synchronous machines that were basically soaking up that unbalance are being retired, and we're left with devices that don't do unbalanced control in steady state. So the unbalance is rising in the system, which is potentially going to start hurting synchronous machines again. When you add grid forming resources back in, and we found this kind of by accident in Hawaii, that starts to soak up unbalance again. Okay, so it's helping to add that margin back into our system that we didn't even know we were using, right? So the unbalance problem that we don't know we have yet is potentially going to be solved without anybody noticing that we had it. And cybersecurity and all of that, of course, is the same. So we can, oh, dang it. All right. Functional specs. Oh yeah. So NERC issued a functional specification for grid forming a while back. It was quite a good document in that it was deliberately simplified. So it said, here's a functional spec. This is what you can ask for to get grid forming. And I still like that document. You can use it to, if you don't have a specification for grid forming, you can say, this is what we're asking for when we ask for grid forming. But at the end of the day, if you want to specify grid forming, you really need to specify tests. So you need to say, this is what we're going to do to test your equipment and make sure it's robust and gives us what we actually wanted. So functional specs are fine. Tests are stronger, in my opinion. So you can say what you want for legal reasons, and then you can go back and test that you're going to get that. I don't think I'll say much more about this because we talked about it in Alex's slides before, basically thinking about when you want your energy and when how your overall frequency profiles look in your system will determine how you specify frequency response and what kind of energy you need and when. So balancing rock off against sort of primary frequency control and all of that. Additional points, currently commercially available. Cost is expected to be marginally higher. Existing GFL BESS may or may not be upgraded to GFM at a future time. So this is something actually, if you are afraid of grid forming, at least what you could do is say, we want you to be operated in grid following mode for now, but we want the ability to change to grid forming later. Okay, that may be a sort of a halfway point that you could avoid sort of all that lost opportunity. And this is out of date now. Two StatCom vendors is correct. Yeah. So ordinary StatComs are also being offered with grid forming. Now that's a little different from a battery because they don't have a significant energy source there. So generally you should think of a StatCom with grid forming as being kind of operating only in one axis. So they can do grid forming on voltage, not so much on active power, right? Not currently available in PV or wind. I think PV, there is some stuff out there kind of being talked about. And also wind, I know GE had a lot of research going on, and they were doing some work on a test facility that I think got canceled in this last year. But it seemed somewhat promising, basically taking type 3 turbines and using a little bit of their inertia to make a grid forming controller.
Yeah, the big thing for those two, for PV and wind, is that there's much less energy stored, right? PV has none, and wind has very, very little.
Yeah.
And when you squeeze energy out of a type 3 wind, you have to give it back, or else you rip the blades off. So like you would have you had a graph of it kind of looks like FFR, where it would go up, you get a little bit extra power, and then at some point you got to get energy back to avoid.
Yeah. Although you could also take the same route as the StatComs and say, we're not going to give you any active power or angular stability, but we'll give you voltage magnitude stability. So you can hold the voltage constant and you get that small signal voltage stability, which will really help you in weak grids. We've seen that in the StatComs without any real energy behind it. So it's basically like operate your voltage source converter controls like a StatCom a little bit, or like a grid forming StatCom. So it's like half grid forming, right?
Yeah,
but
we always talk about under frequency events when we talk grid forming, but without the extra energy, you can still respond to an over frequency event. You don't need extra
over
energy.
frequency and voltage.
Yeah, exactly.
Right.
Yep.
So you can resist voltage changes, which is one of the main sources of instability that we have.
If you can convince someone to do that, you could. Yeah, exactly. Yep.
Oh, with the
Yep.
voltage, like
With
you need
headroom.
to have reactive power headroom there.
He mentioned you can use headroom, but headroom is a solution, but that's a hard one to require it and that kind of stuff. Yeah.
Yeah, you can incentivize it or you can require it again, but most of the time people are trying to incentivize it if you want headroom. Okay, I think I can stop here, or I can go a little further into some of the tests. But it's a bit more of a technical discussion. I think I'd rather probably pause unless you guys really want to go there. And
everyone
then
looks a little tired.
sort of wrap up a little bit.
I got 2 nods.
What's that?
I said everyone looks tired. I got a couple of nods there.
Yeah,
maybe
that was a pretty dense couple of hours I gave you just now, so that's totally understandable. Maybe I'll pause here and just say we can have a bit more of a wrap up or opening or closing discussion about the course.
Well, I mean, I don't have much to close up. We have the room until another half hour, right? So we could have more open discussion if y'all want to do those. And if we run out of questions, I'll just wrap us up. So I guess we'll have a little abridged shortly. I guess about the same as yesterday. So any questions like the last 2 days? Deeper questions into topics? Yes.
So I have 2 questions. One is, can you clarify whether are there any concerns for grid forming batteries? Like, assuming that the modeling was done right, with the right models, we verify that the equipment is right and has the right controls. Is there any concern about batteries?
Okay, so generally, and so we've done a lot of testing with very detailed models of grid forming controls. So all the major manufacturers, we've done tests. We've built a lot of tests to sort of exercise them. I would say generally they behave very well. And since we're doing testing, we tend to try and break things, right? When you're doing testing, we build the tests as extreme as we can and try and break them. And we generally can break them. Okay, so that's, to be fair, we can break a grid forming controller if you make us break it. But those tend to break far later than a grid following. So the tests we're applying to the grid forming device would destroy a grid following device long earlier. So they tend to be very robust and behaving very well, even if you don't do much to them. That said, you need to test them because sometimes somebody does a bad controller. They make a mistake with their controls and the controller won't work properly. It'll do the wrong thing. And so just like any grid following device that you're going to put in the system, you should be testing it at strong system, medium system, weak system. All of those things that we would do for a grid following device, you should also test for a grid forming device. The other thing I will say is that we can't break the laws of physics with grid forming. So if you're going to go to SCR of 0.7 in a fully inductive system, you're going to collapse your voltage, and there's nothing the grid forming can do about that. Right? We can't break the basic transfer laws that we have for power transfer and angle. So grid forming, sometimes we get the sense that we can just kind of, it's a super weak system. We just put a grid forming battery there and it'll solve this transfer problem that we showed with the voltage collapse. That's not true. If you break that law of max power transfer, your voltage is still going to collapse. So that's actually caused a little bit of problems in some regions where people weren't expecting, voltage collapse with this nice grid forming device. So that's not really the fault of the grid forming plant. It's more of a fault of our expectations. But
yeah, the huge consideration too is the more grid forming you get in a small area or a weak grid or a lot of grid forming in a strong system is there are really aggressive controllers. So
not aggressive controllers.
Or sorry, they're just aggressive. They can interact with each other, right? Is what I'm saying.
So the same way as a synchronous machine, if you put a bunch of synchronous machines in an area, do you expect them to aggressively fight with each other?
No, well, they could. Well, it gets into the software base. There's a lot more errors you can make when tuning an IBR, right? And those errors magnified in a many GFM.
So yeah, so maybe to come halfway, they are power electronic devices. And so if you have mistuned those power electronic devices, if you've made a bad control decision and you put them all into service, they can fight with each other and cause a problem. But if you test them properly, they shouldn't. And actually, even naturally, by virtue of the fact that their controls inside are slow, they tend not to. So when we did a study for ESIG, we put a bunch of random IBRs into grid forming inverters in together in a strong system and a weak system, hoping to see them fighting or doing something untoward. And they just tend to sit there. They didn't do anything. So it was very stable. So it is theoretically possible. There's still controllers, but I want to try and fight the idea that they're very fast controllers. They respond very fast, but the controls inside are not actually as fast as a grid following controller.
Yeah. You had a second question, right?
Yeah, so I think that does have implications for like whether we're considering. So I think like ultimately that's the big question is like how do we control it anymore? But if there are some conditions like a extremely low short circuit ratio that could happen at some point in the future on a grid, then we need to just make sure that there's some protocol in place to restudy under certain conditions or something, like if we're going to do a requirement. Alternatively, we would have to be able to like quantify the benefit of getting these grid forming services and then incentivize that.
Yep. What Andrew said earlier is super important, which was you can require the capability but not turn it on, right? So that's a middle ground, right? So you can. No, I mean that's the difference between. Well, that's the difference between not having like normal everyday controls like AVR turned on and not having turned on this more advanced, less tested control on. Mm-hmm. Oh, well, in that future paradigm, if you need GFM, then incentivize it to be there all the time. But right now, a middle ground that kind of works a little bit in the discussion is if you're uncomfortable requiring every best to be enabled with GFM right now, the middle ground is to say just require capability and show me you can do it at some point. We may ask you in the future, and that's been like a proven success in some areas for other advanced features as well. But every day if you don't do that, the opportunity cost is huge, right? If you get to a point where you need a GFM and you didn't do the requiring of the capability, then we have all the other problems of trying to go back and does it even have the capability? What does it cost for the developers who've already assigned their service contracts and all that type of thing? So the opportunity cost is huge. So there's just, in my mind, the best is to require it. Second best is capability. Third best is just we'll wait.
I got two more questions in the back, but I want to add one thing. Actually, you keep sort of worrying about the ultra weak systems. Actually, with grid forming, it's a little bit backwards. The ultra weak systems, they work beautifully. What people are often worried about, and this is because of a little bit of misinformation, but they're worried about, and you may hear this, what about really strong systems? We heard that they're unstable in really strong systems. And there is some truth to that, but it's kind of it's a special sort of problem. So I just want to quickly put that to bed. There was one of our researchers did his PhD on this topic, and he published a really nice sort of analysis of it. If you have a very strong system or even an infinite system, and you have a very high inertia synchronous machine or any kind of machine with a high inertia, you can turn up that inertia until you drive it unstable. Basically, you'll start to see a very high inertia into another very high inertia. They can be unstable. And you can do that with a grid forming controller as well. If you turn the inertia up too high in a strong system, you can make it oscillate and have trouble damping. Two things about that. One is that if your system is very strong, it's still oscillating against a very strong system. You won't see it in the voltage. So it actually isn't moving the system, it's moving itself. But the second thing is that's a poorly tuned GFM that you can test out in the beginning. One of the risks, and in this discussion of verifying, one of the risks of asking for inertia is you want to avoid people giving you a ton of inertia to meet your requirement and driving themselves unstable. So there's a range of inertia parameters that are kind of optimal for grid forming that will work in any system. And most of the commercial ones are tuned that way, so they work in any system strength, and we can test it easily. But if you incentivize inertia too much, people will give you too much inertia. They can drive themselves unstable, and then in that case, you have to have other tests that balance it and make sure that they're not unstable in some other way. But so it's the strong system one that people are more worried about for grid forming than the weak systems. But okay, two questions back there. One.
So I guess just for that, has there been any concern to batteries that lead to an increase in the degradation of the life cycle, especially if oscillation damping?
Yeah, it's a good question. I think it came up the other day as well. I think so. My information that I've gotten on this is that what's happening with the batteries with a grid forming controller is you're cycling your current potentially all the time, or if it's damping oscillations, you're moving your current in and out. But that doesn't actually move the state of charge on the battery at all. And so moving current in and out of the battery within its ratings is fine. Moving the state of charge significantly in the battery will degrade its life. That's my simplified understanding of battery chemistry. I've been asking this question and nobody's telling me it's a problem. But it's a fair question, I think.
The other consideration could be maybe more wear and tear on the balance of plant equipment, but
if it's moving a lot.
But I don't even know how you. I mean, that's similar to what we talked about yesterday, the on-load tap changers and how fast you want it and how that could degrade life. But I don't know if we haven't had any of these running long enough to see if the transformers are lasting 5 years now instead of 20 years.
Yeah, and Tesla is now actually recommending all of their batteries be grid forming. So that's their own experience, and that's because they're seeing better stability from their plants that are in service for grid forming. So they don't think it's a problem. So
unless Tesla's going to start selling transformers now, right?
What's that?
They going to sell transformers and balance of plant equipment advertised?
Yeah.
No.
I don't know. Maybe, yeah, I don't know. Maybe it's a marketing angle. I don't know, but
You can always add serious capacitors.
It
Next.
fits everything.
Have you done any full-time field study for solar plus storage systems?
Yeah.
To see the interaction between GFL and GFM?
Yeah.
Is there any interaction between doing both right?
I mean, you put a fault on and they both have a ride-through profile. The grid forming will stabilize the system, so the fault ride-through for the grid following will be better. Right? So if you had a problem with a weak system where the grid following was having trouble recovering and you put a grid forming battery in, it will now be more stable. So that was one of the examples I showed on there. And also the ESIG study did a lot of work showing basically capacity unlock for grid following devices. If you put the grid forming batteries next to them, they unlock extra short circuit capability basically. So it just helps them.
And then after that, you still have the same. It's basically the same exact thing as two grid followings at the same plant. You have to coordinate the controls, the slower controls, the primary controls as well. But that's an old problem. But the GFM specific problem is what Andrew just mentioned.